So previously we had looked at how if you have dt graphs, you can actually get the speed from dt graph being the slope. So we looked at, you get your basic dt graph, and of course the slope was equal to the speed. And of course, so then, speed would be the change in d over change in t, which is the variation of the rise over run, or the delta y over delta x. There's no real difference between it. So of course, most people don't really think about it like this too much. Most people just drop the deltas when they actually write it, and most people just remember it as dTV, because a lot of times it's a lot easier to remember expressions when they're flat than like a multiplication compared to being a fraction. So this is what we sort of looked at last time. Well, we're going to practice with this a little bit more, except more like traditional type setup, which is like basic scenario type questions. Nice and basic stuff, nothing crazy, nothing too weird. Just get going here. So let's take something really, really simple. Let's get the road, and let's just draw a little car. Okay. All right. So there, I got a little red car puddling along, and let's say it's cruising along, and let's say it's going at, let's go with 50 kilometers per hour. So basic speed, 50 kilometers an hour, like in a neighborhood or something like that. Okay. And let's just do something really simple. Okay. How far would it go after 30 minutes? Okay. Now, one of the basic things to always check for is units and things, matching up nicely. We got 50 kilometers per hour. There's nothing really wrong with that. We usually will typically be using meters per second, but there's nothing really wrong with kilometers per hour on top of things like cars and stuff like that. No big deal. So the 30 minutes doesn't really click very well. Nobody uses minutes for anything. It's either seconds or hours. Minutes are just dumb. So the easiest thing to do would to be convert that into an hour, which of course is 0.5 hours is probably the easiest thing to do. Okay, so we'll just convert that out. All right, so now we're able to then look at our solution. Now we're looking for the distance, and you only have one expression for distance so far, dTV. You got time times the speed. Well, you've got the time, you've got the speed, you just got to put them together. So with that, you've got the 0.5 hours for the time, you got a speed of 50 kilometers an hour, and doesn't take a whole lot of math power. 0.5 times 50 would be just 25, and this was done in kilometers, so 25 kilometers. Okay, so relatively straightforward, no big deal. Now, along with this, though, we're sort of isolating like the four main things we're looking for in a basic solution, especially when you're starting with physics. I'm looking for formula, substitution, answer, and units. I want all four things, especially when you guys are starting out, all four things for every calculation that you guys do. Now, as you guys do more and more and more, you get better and more comfortable, we'll start backing off on a couple things, like showing every substitution, stuff. That will sort of tone down a little bit, but especially when you guys are starting out, when you've only got like one, maybe two formulas, formula, substitution, answer, and units. And try and keep it organized, moving down, maybe to the right and down or something like that. Don't be going like moving your solutions towards the left, or like going up and stuff like that, some kind of way. It's either to the right or down, and depending on the length of the solution, you sort of figure things out. But you don't want your answers going all over the place. Okay, they should be nice and sequential. They should be nice and tight and organized. Don't go all over the place. Have things all nicely tied together. Especially when you guys start doing questions with like 3, 4, maybe 5 steps. If you're going all over the place, it's just going to be a disaster and a mess everywhere. So we want to try and keep things as tight as we possibly can. Okay, all right, well, let's try something similar, a little bit different, no big deal. Okay, let's try something else. Suppose we've got, there we go, all right. Okay, so suppose we've got a B, there you go, so a giant B, and our B is flying along, and let's say our B goes, let's go with 120 meters. And I guess this could be a relatively fast B. Let's say it goes 120 meters, and let's go with in 45 seconds. Okay, so what is the What's the speed of the bee? Okay, so this time we're looking for speed, which is like the slope when you guys did your graphical type stuff. Okay, so if I'm looking for speed, of course, the symbol for speed is a V. And I mean, the expression's right here. And most people often don't write the deltas. We're not going to worry about it too much right now, but a lot of people don't write the deltas. Just d divided by t. So there's my formula. So now I can go with my substitution. I got meters and seconds, so I'm not worried about units at all. We're all good. So we've got 120 meters. We've got a time of 45 seconds. And now we just have to punch that out, and we will have our answer. So we got 120 meters, and we divide that by 45 seconds, and we get a value of 2.7 meters per second. Now, when I punched that in my calculator, I got like 2.666, and it kept on going. This goes back to what we talked about a little while ago, significant figures and rounding. Don't give me 2.66666 because that's what your calculator showed me. Don't give me 2.6667, 2 or 3 sig figs. 2.67, that's fine. 2.7, fine. 3, not so much. You're over like 10% off if you put 3. Okay, so 2 or 3 significant figures at the end, and you will be perfectly fine. Okay, so there's a couple basic questions right there. All right, so let's look at a couple other different scenarios. So let's clean this up. Let's get rid of this stuff and look at a couple other questions and just do some more fundamental type things. Okay, so let's take this. Let's go with, there we go. Let's go with this. We're going to go with an airplane. Okay, so we've got an airplane and it's traveling along, something like this. And let's say our airplane is going, let's say our plane is traveling at 175 kilometers per hour. Okay, so how far will it go? How far is this one going to go in, let's say, I'll give some time here. Let's say 860 seconds. So how far is our plane going to go in 860 seconds? Okay, so first thing, a quick little check here. I got kilometers per hour and I've got seconds. Those don't match up. You know, if you're not sure if you should change the kilometers per hour into meters per second or the seconds into hours, when in doubt, use meters and seconds. You can pretty much never go wrong with meters and seconds. So I want to change my 175 into meters per second. Now, basic conversion, I mean, there's 3,600 seconds in an hour, and there's 1,000 meters in a kilometer. You put the 3,600 and 1,000 together, you divide the two out, you get a conversion factor of 3.6. And that's a really good conversion factor to plug into your brain and store in there, that the conversion factor is 3.6. So all I have to do is take that 175, and I just have to take that and divide that by 3.6, and I will have a speed of 48.6 meters per second. So just using the conversion factor. Okay, so now that my units sort of match up all nicely, now I can do my basic DTV. I've got my time of 860 seconds. And I've got the 48.6 meters per second. So then I'll just multiply those two out. And if I do that, I will get, give or take, we'll round off again because we're supposed to, right? Around 41,800 meters. Okay? 3 sig figs there. And if you had done this in kilometers per hour and changed the seconds to hours, no big deal. You would have gotten like 41.8 kilometers, which is literally the exact same thing. It doesn't really make that much of a difference. Okay? All right, so let's try something a little bit different and also a little bit similar. Okay, well, let's see. How about this? So we've got some water, and there's the beach over here, something like this. There we go. Over here. Let's go with, there's your little boat in the water, a little motorboat. Unfortunately, you have run out of gas, so here you are, swimming along in the water, getting to shore because you ran out of gas in your boat, so you're going to go get some, I guess, I don't know how you're going to swim back with gas tank, but whatever, we'll figure it out, no big deal. Okay, so here you are. swim along, and let's say you are swimming at 0.72 meters per second, and let's say that you are, give or take, let's say you're 35 meters away from shore. So how long is it going to take you to get to shore? Okay, so this time we're looking for time. We're looking for t, we're looking for how long. So we're looking for t. So our basic expression, of course, it's right here, dtv, we're solving for time. So we got to divide by the v on both sides, so that'd be distance divided by v. So we got a distance of 35 meters. The speed is 0.72. So we just got to take that 35 and we'll divide that by 0.72. And we plug and play. And we're looking at around 48.6 seconds. Okay, that's not too bad, actually. Okay, that wouldn't be too bad. If you're swimming less than a minute, that's not too bad. Okay, you're not too far away. Okay. Okay, so now let's look at similar type of stuff. Okay, except let's see if we can go up a little notch here. And actually, it's going to be very, very similar to what you were doing with the graph type stuff. Okay, so let's see. Well, we'll do some water stuff. Sure, why not? Okay, so here's some, we're going to go underwater here for a little bit here, just for fun. And we're going to have, let's see if we can draw this okay. Let's use this. Okay. Got some stuff going on over here. Little coral reef type action going on over here. Some coral type stuff. Lots of different colors and some of those weird things that grows off the coral. No big deal. And over here, let's draw. Here we're going to have a nice little fish. Okay, so here's my little fish over here. There we go. Okay, there's my little fish. And we're going to have him swimming towards the right. So we got a little fish over here. And our little fish is going to swim to the right. And let's go and say it's going to go 1.2 meters per second for, let's go with 6 seconds. So it's nice and simple. So it's going to go 1.2 meters per second for 6 seconds. Okay. And then what's going to happen over here, all of a sudden, okay, sees a big mean, well, say I guess a shark or whatever. All right, of course, which is going to scare a little fish. All right, something like that. Okay, so big mean fish over there. So our little fish is going to go towards the right at 1.2 meters per second for 6 seconds. It's then going to get scared by the big fish. It is going to whip around and head back to the coral reef for protection. And it's going to fly back at the coral reef, and it is going to go at 1.8 meters per second for, let's go with 3.5 seconds. Okay, so this little fishy is going to swim at 1.2 for 6 seconds, gets scared by big fish, and then rips back to the coral reef going 1.8 for 3.5 seconds. Okay, so there's two parts of the situation. One where the fish is going forward, and then it's going to come back a little bit. Okay, so we're just going to start basic stuff, no problem, just once. We're going to sort of piece this together. So first things first, what was the first distance that the little fish traveled? So how far to go during the first part? Okay, well, for that, I'm just going to look at the first part stuff. This is a V over here, but I'm going to call it V1 because that's my V that it had at the beginning. That's my first V. And this is a time, and I'm going to call that T1. Now, subscripts come in really, really handy. Subscripts are really, really important, especially like multiple times, distances, V's, which easily happens all the time. Subscripts are really, really, really important. The same way I could call this the second V and the second T, okay? And it just helps me keep things nice and organized, all right? So the first distance that my little fishy traveled, I want to know the first. Well, I'm actually going to do that over here where it actually occurred. Over here, distance 1 is going to be T1V1. It's just basic DTV using my first time and my first speed, my 1.2 and my 6. So the first time was 6 seconds. First speed was 1.2. So I just have to multiply those two together, and I get 7.2 meters. That was the first one. And I often like to put my stuff where it belongs in the situation. That's where the fish was. That's where that speed and time was. That's when that was occurring. I like to try and keep my stuff together. So there's my answer for that one, 7.2 meters. Okay, all good. Well, let's just do the same type thing. So what was the second D? So what was D number 2? Okay, well, that's going to be pretty much the exact same thing. Okay, so distance 2 would be my second time multiplied by my second speed. So I've got that 1.8 and I got 3.5. So 3.5 seconds, 1.8 meters per second. So all I have to do is time those two out. So we get 3.5 and we multiply that by 1.8 and we get 6.3 meters. So it's going to be 6.3 meters would be my second distance. Okay, so that's all good to go. All right, now let's get a little bit more compared to or similar to what you guys do with the graphing type stuff. What if for the entire thing, I asked you, what is the average speed for the entire thing? Okay, so there's just like the graphing stuff that you guys did. There's no difference. When I got to the average speed, I'm not just going to take the 1.2 and the 1.8, add them up and divide by 2. I'm not just going to add them up because the two speeds didn't last the amount of time. It doesn't work that way. If remember, when you're finding your average speeds and velocities, you just add them up and divide by 2 like that all the time. So what I want to do, if I want my average speed for the entire thing, remember, I want to use my total distance and my total time, okay, for the entire thing. So if I look at my total distance, first my little fishy went 7.2, then it went 6.3. So that's a total distance of 13.5. So 13.5 meters altogether. Total time, well, 6 seconds, 3.5 seconds, so that's 9.5 seconds. So we're going to divide the two out and see what we get. So we get the 13.5, and we divide that by 9.5. We get an average speed of 1.42 meters per second. Okay. Now, just like when we do the graph stuff, what's the average velocity? Okay, of the entire thing. Okay, so this is same type of thing. Don't add them to divide by 2. Very similar to what we just did, except for average velocity. I like to write my average velocity like that. And I'll write my D's and T's like this, just so I can have a difference between them. I don't want my total distance. I want my total displacement. Now, my fish went 7.2 meters to the right, and then it came back 6.3 meters. So if I look at my displacement from where it began to where it ended up, it only moved that little tiny distance right there. It only moved like 0.9 meters. That's the displacement, is 0.9 meters. From beginning to end, it only moved 0.9 meters towards the right, and that's it. Okay, so if I can look at that distance, that displacement right there, I got the 0.9 meters. .9 meters, and the time is same time, 9.5 seconds. So we just divide the 0.9 divided by 9.5, and it gives us 0.095, that's kind of weird, meters per second. That'd be the average velocity. Okay, so there's no difference. It's sort of like when you guys did the graph stuff, and you had the graph, and it looked like this. You know, you had one line like this, and then you had another line that, you know, changed direction or something like that, like this. We look at the total distances, total times, total displacement, total times, and divide those two out. Okay, similar to that. Okay, so there's a little practice with finding averages in terms of velocities and speeds, as well as the basic calculations, that type of stuff.